Well, hello everybody who is here so far participating in this webinar. Thank you for joining us. This is Brian Benish with DSIAC. Got Zachary Quinn on the line with us, who will be giving his presentation shortly, but I just wanted to spend just a few moments giving you all an introduction to DSIAC, who we are, what we do, and then kind of a lead into why we're hosting this webinar. Before I do all of that, let me just go through a couple logistics with this platform and a bit of a fair warning. This is our now second time using this platform for webinars, so we're still working it out and making sure we know how to use everything. So one thing I want to point out to everybody is that if you haven't already recognized, if you are coming in muted, unfortunately that's just a feature of this, which ends up the system that helps us actually make sure we have no feedback. So kind of apologize for any inconvenience there, but if you are dialed in and you're looking for the presentation, you can download a PDF of the presentation through our website, and that just go to the DSIAC.org under resources, webinars, and you can find this on this webinar's web page. It has a little download link for the PDF for the presentation, so you can follow along there if you'd like, if you're only dialed in. For those who are joined in the AnyMeeting platform itself, you should see a series of buttons and features in it. The one I want to draw your attention to is a little icon, kind of looks like a chat icon towards the top of the screen, should be above the presentation, I believe. It says audience questions. Throughout the presentation, if you have a question, I would encourage you to type it in there and not type it into the chat. So we're going to go through at the end of the presentation some of the questions we have, but we'll be looking in the list of questions that come through view audience questions. So if you have a question, again, click that little audience questions button. From there, you'll just click add a new question, enter it, and then we'll go through them at the end of the presentation. Hopefully that makes sense to everybody. Okay, so in terms of DSIAC, who we are, what we do for the Defense Systems Information Analysis Center. So we are a component of the DoD Information Analysis Center program, a kind of larger entity. We're one of 3 IACs, Information Analysis Centers, in that program. CS and HD are our sister organizations. The distinction amongst us is going to mostly be based on the technical focus areas. Each of the IACs, CS, HD, and us, DS, are chartered with a set of technical focus areas, one of which is directed energy, probably most relevant for today's presentation. But the reason that the IACs are in existence and is to help those who are in the DoD or doing defense-related research and engineering find the information they need, help reduce mitigate, I'll say, the redundancy that can occur and does occur within the DoD research engineering landscape, and help foster some collaboration, stimulate some innovation in that work that's being done. So organizationally, we are under DTIC, DTIC, the Defense Technical Information Center, which is essentially the DoD's technical library. It's got millions upon millions of reports and documentation from anything that was produced under, at least in part, with federal funds. So if you're looking for any defense-related research reports and findings, DTIC is the place to go. DTIC, however, is recognized that there's so much information there and so much information even further that's available to those who are doing research engineering that they've stood up these information analysis centers to help folks find the information they need when they're conducting their research efforts or engineering efforts or development efforts that they're either planning or already in the midst of conducting. And so that's why we're in existence. Probably the chief service we offer in that regard is our technical inquiry research service. So it's a free service, fully funded by DTIC already to our organization. We've got technical folks on staff who are ready to help you find information you might need. And so you can submit a technical inquiry to us, some sort of technical question based on whatever topic you might be interested in. And we will go out and try to find the relevant information to help give you a head start on whatever effort you're working on. So if you want to get ready to do some USPL type research effort, before you go off and spend who knows how much money and time doing it, you might come to us and say, hey, what else is out there? Has anyone done any work similar to this, or have anyone solved this sort of problem before? And again, we've got technical folks on staff who will be able to find the information you need, and again, give you a head start on that. So that's probably the chief service by way of helping to find information. But we do want to try to be proactive to get information out to the community, so there's a general awareness of what's being done. And so that's what these webinars are all about. We're getting folks who are doing work in the DoD research and engineering world to present their work, create greater awareness, and hopefully create some collaboration that might come out of this. And so Zachary has been kind enough to join us and give his presentation, and I've blabbed on here for quite a while, so I will hand the time over, the rest of the time over to Zach for his presentation, and then I'll chime back in at the end to help moderate some of the questions and answers. So Zach, all yours.
Thank you very much, Brian. My name is Zachary Quine. I'm a research physicist at the Army Research Lab in Adelphi, Maryland. I'm going to talk to you today about the characterization and study of filamentation of ultra-short pulse lasers in transparent optical materials. And I'm just going to jump in and get started with no ado. So the purpose of this work is to measure and characterize the nonlinear optical effects that take place when an ultra-short pulse laser propagates through transparent optical materials, and begin to map out the broad parameters. Sorry, got distracted by the messages. Gonna not focus on those. Purpose of this work is to measure and characterize the nonlinear optical effects that take place when an ultra-short pulse laser propagates through a transparent optical material, and begin to map out the broad parameter space of laser controls to better understand and control these effects. Quickly outline the talk. I'll begin by giving an overview of some background concepts and context to convey why we're interested in these phenomena and how we study it. Then I'll present a selection of results we've collected and discuss what we can learn from these experiments. The next slide. In recent years, there's been rapid and significant advancement in the development of ultra-short pulse laser sources, making it critical to develop the tools and techniques to make best use of these systems and to understand the fundamental physics of the unique processes taking place at the extreme intensities reached by these femtosecond laser pulses. Processes like self-focusing, self-phase modulation, supercontinuum generation, and filamentation, which is kind of a culmination of all of these. These effects have been studied fairly thoroughly within a few narrowly defined domains, especially propagation of 800 nanometer lasers and propagation in air. But once you step to longer wavelengths or try to look at more complex condensed phase materials, the high intensity propagation regime is still not fully understood. And that gives us room to explore. Next slide. So this work looks at, so now I'm going to give a bit of background tutorial on filamentation. And I'm going to apologize up front. This may be obvious common knowledge to some of you or still not clear enough for others. Usually I can gauge the room and figure out where people's eyes start to glaze over, but I can't see any of you. So I'm just going to try to aim down the middle and hopefully keep most of you on board. Filamentation begins with self-focusing. When a laser propagates through a medium, it sees an index of refraction, and that index of refraction is dependent partially on the laser's intensity. With a spatially varying optical pulse, you get a spatially varying refractive index, which imparts a spatially varying optical phase, which is a virtual lens. And that causes the beam to collapse in on itself. This is actually the effect responsible for Kerr lens mode locking, which is the process that's responsible for the generation of most of the ultra-short pulses in a lot of femtosecond lasers that we use. But above a certain critical peak pulse power, beyond focusing down on itself, it can actually continue to focus down and until it completely collapses in on itself. Except that is stopped because nature hates a singularity. So what happens next is even cooler. These higher order nonlinear interactions that would normally be weak begin to activate and provide an opposing diverging term that causes the beam to stop focusing and expand back outwards. The balance between this self-focusing and higher order defocusing terms causes the laser to kind of surf this wave where it balances and propagates for this extended propagation length in this confined high intensity region, and that's what we know as the filament. The critical power where this occurs is given by the relationship in the lower right, and is inversely related to the index of refraction and nonlinear index, and directly to the square of the wavelength. And the distance that this balancing begins to occur, the origin of the filament compared to the geometric focus, is given by the collapse length. That's the ZC relationship given on the right. This term becomes important later, and I'm going to return to it. So as the laser propagates through a material in this extended, confined, high-intensity filament, it is the perfect environment to enhance nonlinear optical interactions. Normally, weak or discouraged interactions grow, and so we see this blooming through self-phase modulation, four-wave mixing, stimulated Raman excitation, harmonic generation. All of these normally weak effects become very strong because you've confined the laser to interact with the material for a much longer length and a much higher intensity than it normally sees through just regular focusing. By measuring and fully characterizing this emission, we can try to work backwards and deduce what is happening during filamentation. And in the next slide, I'll show the experimental setup we use to achieve that. At the surface level, the experiment is actually fairly straightforward, although there are some key details that make the experiment interesting and challenging. We start with a titanium sapphire femtosecond amplifier. That's the coherent legend elite in the lower corner, which gives us 35 femtosecond pulses with a kilohertz repetition rate and about 3 millijoules per pulse. That drives our topaz white optical parametric amplifier with near UViz and in DFG frequency shifting modules that gives us a continuously tunable femtosecond source, producing femtosecond light from the 250 nanometer ultraviolet out to 10 micron long wave IR. This is one of 3 femtosecond laser systems we have in our labs. We also have a second similar kilohertz 3 millijoule system from Spectrophysics, and a high energy 10 hertz 100 millijoule per pulse. So it's 30 times the pulse energy with a similar optical parametric amplifier and frequency shifting modules that allow us to reach UV and long wave IR with much higher pulse energy that we can move over to if we need more power at longer wavelengths. So we take this tunable ultra short light pulse and focus it into a sample of interest. Once focused in, it undergoes a cascade of nonlinear optical processes, ending in filamentation and generating this broad cone of white light. We collect and analyze this light using an array of spectrometers. In these experiments, we're using 3 spectrometers with detectors spanning the ultraviolet to the long wave IR, and we stitch these, in order to stitch these spectrometers together, great care was taken in the calibration of the spectral response function of the spectrometer detectors, as well as all intermediate filters and optics to ensure that the signals produced are reliable, quantitatively accurate measurements. That's what enables us to fully characterize these extremely broad bandwidth light pulse or beam light pulses. Further, we use a scanning pinhole aperture to spatially resolve the measurements to generate 2-dimensional spectrograms like the one on the right, which reveal complex structure that gives information about the underlying processes occurring during filamentation. On the next slide, I'll show some selected results from these measurements. Oh, no, on the next slide, I'll show some of the samples of interest that we are working with in these experiments. So we're beginning by looking at just common optical materials. We're looking at sapphire and zinc selenide, fluoride glasses. All these materials have broad transmission windows and are commonly used in optical instruments. We've also listed some relevant optical parameters for reference, and wanted to note that this is the middle of an ongoing program, and as we move forward, we intend to study many more materials, as well as to look at how things like sample quality and makeup impact the supercontinuum generation and filamentation. So now I will get to selected results. Yes. So again, looking at calcium fluoride, we see that the supercontinuum spectrum generated by filamentation of 800 nanometer light laser beam on the left and 1.3 micron on the right. These are both spectra generated by filamentation in a 4 millimeter thick calcium fluoride sample. They both show broad octave spanning supercontinua with the shortwave side. That's the supercontinuum with frequencies with wavelengths shorter than the initial laser pulse, having a broad flat plateau that kind of terminates abruptly at this multiphoton absorption threshold. And on the long wave side, with wavelengths longer than the initial laser pulse, you see kind of just an exponential tail with no clear termination. We can track the, why do I keep using the arrows? We can track the total integrated intensity in both of these portions of the spectrum to extract threshold pulse energies to observe filamentation effects and observe scaling rules for the supercontinuum conversion. So you can see that the conversion efficiency from the primary into the supercontinuum intensity increases monotonically from this threshold pulse energy below which you don't observe any effects. If you take the temporal pulse duration associated with these pulses and plug it into that pulse energy, you'll see that it's actually higher than the critical pulse, the critical power theoretically associated with filamentation. And that is due to the finite propagation length available in these material samples. The critical power gives you the peak intensity, the peak power needed to see filamentation in an infinitely propagating medium. But in these samples, we only have a few millimeters to see an effect. And that's where that collapse distance from earlier comes in. So basically this drives home that in materials, in finite samples, the observation of filamentation and the yields that you can expect to get and the properties are not going to be reducible down to a single scalable parameter. You're going to have to take into account information about the sample makeup, geometry, focal geometry, wavelength, and intensity, as well as wavelength and intensity of the laser. But we can track these, track the supercontinuum generation and extract these threshold pulse energies for a given sample geometry and composition. We look next at magnesium fluoride. Yes. This is magnesium fluoride is qualitatively similar to calcium fluoride. We see the same broad, flat, shortwave supercontinuum that terminates at a multiphoton absorption edge, and the same long wave behavior. It takes a higher, same long wave behavior. It has a higher pulse energy threshold to view filamentation, but if you compare it to the critical power, you can see that this is because of the lower nonlinear index, and we see actually a similar ratio between this threshold pulse energy and the critical power, which I'll get back to which I'll come back to. We'll see repeated as I continue. Next, we can look at Sapphire. Sapphire is interesting. It has the highest conversion efficiency and the broadest supercontinuum of the materials studied. This is kind of expected. Sapphire is a common sample used for supercontinuum generation as seeds to OPAs or in transient absorption spectrometry systems. But what's interesting about observing and analyzing this supercontinuum, especially excited by the 1.3 micron OPA, is that this is near the 0 GBD wavelength for sapphire glass, which means that the underlying physics of the filamentation and propagation are different are different in this 0 GBD region or anomalous GBD region, or anomalous dispersion region. And you can notice that by looking at the nature of the spectra. Whereas in the fluoride glasses, you had a flat plateau that terminated at a multiphoton absorption edge. In this, you see it's almost like the shortwave spectrum has separated off and is slowly blue shifting as you increase the intensity. And that's because that's actually what is theoretically seen to be happening. You get a fundamentally different pulse separation process. And being able to collect and absorb these spectra gives us the ability to differentiate these different propagation regimes. Moving on to zinc selenide. This is also a unique material because, unlike the others, it has a stronger Chi2 nonlinearity, causing it to favor harmonic generation over continuum generation. This, as well as being close to the multiphoton absorption edge at 1.3 microns, means that even though zinc selenide has a much higher N2 and expects a much lower critical power, the filamentation threshold pulse energy is much higher compared to the other samples studied, and we don't see nearly as much supercontinuum generation because all of the intensity is being funneled into harmonic generation and two-photon fluorescence. I'm just going to move on. So as we repeat these measurements across multiple samples and source wavelengths and peak intensities, we can begin to see conserved trends between all of the materials. In the table on the left, we can collect all of the measurements taken on samples of the same thickness and the same focal geometry with different materials, laser wavelengths, and a range of pulse intensities. And what we see is this consistent conserved multiplier scaling the threshold pulse energy to view filamentation effects in a material compared to the theoretical critical power, this around between 4 and 5 times the critical power to see threshold filamentation. We can also look at varying the sample thickness and see that we still see this same conserved multiplier that follows consistent trends as you vary the sample thickness. What all of this shows is that for filamentation in finite materials, you get this more complex behavior where you have to take into account the sample and the makeup and the makeup of the sample and the geometry of your target and your incoming beam. And so it doesn't reduce down to just this singular parameter, but there are still consistent conserved trends that can be characterized and extracted and used for future and used to guide future experiments. Oh, I clicked the wrong button and ended the slideshow. Can we get it back? Sorry.
Yeah, we'll get it right back.
Okay.
Here we go.
Sorry about that. So moving on. So now that's all been looking at collapsing down all of the spatial information and looking at just the integrated spectral information to see what that can tell us about filamentation inside of these materials. We can also look at the angle resolved spectral measurements and see what the spatial structure can tell us about filamentation. So again, this is achieved by just scanning a pinhole across the collected conical emission, and at each point taking a full spectrum and then stitching all of those measurements back together at the end. We can generate these two-dimensional spectrograms like you see at the top here. And what becomes immediately apparent is that subtle features that wouldn't have shown up as well in the integrated spectra become glaringly obvious, like these interference banding fringes that you see in a spectrogram of filamentation in a calcium fluoride target from an 800 nanometer laser, about halfway between, right at around the turn on of multi-filamentation. So this secondary point where you go from creating a singular high intensity core to generating multiple filaments that compete with each other and compete with each other for formation priority and intensity. This point, the turnover to multi-filamentation, is an important threshold to be able to characterize, and where it's a little difficult to see in the integrated spectral information. It's, like I said, it's glaringly obvious when you look at the spatial information. So it just shows that the two different domains give different information that can be useful. We can also integrate the spatial features and see how the angular dispersion of the frequencies varies with power and material. So yeah, just repeating, going into the difference between single and multiple filamentation. These are kind of extreme cases of filamentation in two measurements of filamentation in Sapphire, both the same sample, same thickness, same focal geometry, but factor of 10 pulse energy increase, and you go from a very stable, very repeatable measurement with a broad supercontinuum, and still seeing a central core and these wings. You transition from that into this chaotic mess on the right, and being able to, when you look at the spectra of the one on the right, you just see that you're getting much more intensity in the supercontinuum band, and you might, because everything has been flattened down and a lot of information has been integrated out, it's possible to not see that you're entering into this chaotic domain. But when you measure the spatial information, you see this much more chaotic behavior. We can take these measurements and compare directly to simulations. This is an example taken from the literature where you can look at the angle resolved supercontinuum in Sapphire compared to modeling with this that displays this X-wave formation from the UPPE propagation equation, and this basically this is what we're aiming toward, is generating a body of data that we can use to feed into and validate simulation models and give us a better understanding of how the filamentation process occurring in these materials. And again, that missed one. So in conclusion, we've conducted a broad survey of measurements to begin to map out how key laser parameters affect filamentation and femtosecond laser pulses in materials. Moving forward, we're interested in moving to longer wavelengths to see how these filamentation processes change in the mid-wave and long-wave IR bands. We've seen that the underlying processes that take place changes as you move into this anomalous dispersion regime, and further away from multiphoton excitation, you're less likely to see multiphoton ionization, and the processes that are responsible for that diverging optical term that halt self-focusing are different at longer wavelengths, and we're very interested in studying and learning more about that those basic phenomena. We're also interested in expanding the library of materials studied and further exploring more complex laser parameters like pulse duration and beam shaping, but this is just what we've been able to start with. We are interacting with collaborators specializing in modeling high-intensity propagation, and hope that this partnership can guide and inform on both sides, both the experimental and the modeling side. And I'd like to thank all the people that assisted and coordinated with me to complete these experiments, and thank you for your time, and open for questions.
All right, thank you very much. It was great. So we had a couple questions come in through the Q&A portal, I suppose, here on any meeting. So if you have any more, get them in queue. Looks like there's another question in the attendee chat, so I'll work through the Q&A here and then jump back into the attendee chat. But if you do have a question, again, get it in queue in the Q&A chat window here. So the first question, I actually won't read it verbatim because this is a public distribution discussion and topic. I don't want to. We're not able to speak to particular. It speaks of the existence of classified or limited distribution literature and from different organizations. So unfortunately, I'll just skip over that just to be safe and make sure we're staying within the public distribution realm here. So I apologize for that. But the next question here that came in, what is the process taking place at 450 nanometers that reduces power? Slide 15 seems to indicate that SC power increases at shorter wavelengths rather than being further suppressed. That makes sense and come through to you, Zach? Still there, Zach? Just wanted a quick check. Can other folks still hear me, or is this?
Oh, sorry. Yep, I was muted.
Oh, okay. Sorry. Were you able to hear that question?
Yes. So I heard the question.
Slide 15. Let's move over to it if you don't mind. And you're able to view. You should be able to view these questions as well if you wanted to read them on your own.
Yeah, sorry, I was looking at the questions instead of the slides. So I think what you're talking about is the, so you can see it starts to go blue here on the edges. I think that is actually an artifact of the coloring procedure. By beyond 450, this is sapphire. Oh, this is calcium fluoride. This may be harmonic generation 100, but it's very low. It's difficult. The problem with these 2D spectrograms is the three-dimensional nature of them. It's a lot harder to see this intensity data, and so things that are down in the noise start to get difficult to see. The blue here is really pretty close to the noise limit, so it's hard to tell if that is just the because we have to do correcting, because we have to do some correcting procedures as the response of the spectral detectors falls off in the UV, as well as the transmission of some of the interceding filters. Stuff beyond So in this spectral region, starts to get a little noisier. In these, I would say that that is probably not real, that is noise. Anything in the blue.
Okay,
I don't
perfect. Thanks.
think that that's harmonic generation generating 400 in calcium fluoride, because we don't see that there.
Okay, very good. So the next question I had, oops. Oh, okay, there we go. Oh, interesting. Have the investigators done the EM field modeling for theoretical studies of wavefront propagation and behavior to complement this excellent experimental work?
So we are, the experimenter has not, because the simulations necessary to, or the simulations necessary to model these propagations are extremely complex and beyond my simulation background, unfortunately. I have tried, I'm learning so that I can have a better understanding of the model, so that I can do a better job matching it to the experiment. But we are collaborating with two professors from the University of Arizona, Professors Kalasic and Maloney, to look at simulation and modeling of high intensity propagation and filamentation, starting with in air but moving toward materials. We have a few other modelers that are also looking at it. That's unfortunately outside my current realm of understanding, but I am working to better understand the models so that I can make better, interface them better with the experiments.
Okay, perfect. Now let's see, next question. And are you able to see these questions?
Yes, I can see them.
They're showing up on the screen. Okay, just make sure everyone sees them, what others can see. Yeah, have you measured the differences in the spatial characteristics of filamentation among various materials, such as those named?
Yeah, so what I'm directly measuring is the spatial characteristics of the conical emission of the supercontinuum generation. What I aim to be able to do, what I haven't completed or shown here, is to take that information and then go back down to information about the underlying filament that caused that that emission, information about the divergence of the cone, and about you can get information about the spatial characteristics of the filament from divergence of the cone. Is that correct? I think that's correct. And especially once you get into the multi-filamentation regime, you can get a lot more information about how the filaments spatially interact with each other from the spatial interference measurements. So those are I'm taking these measurements of the emission to be able to calculate those spatial characteristics of the underlying filament. I haven't completed that analysis yet, but that is the goal here.
Got it, perfect. All right, next question. Did the investigators use AR-coded windows and study the effects of the relevant coatings?
That is, so at the moment we are looking at just uncoated bulk samples, and there is interest to look at coatings. There's interest to look at a lot of things, and that's where I had a version of the experimental apparatus chart that just went down all of the different variables and all of the different parameters that we're looking at studying, and it felt a little ugly, so I took it out. But it's coatings. Looking at different, more complex materials is definitely on the timetable. Is definitely something we will be looking at moving forward.
Okay, perfect. Our next question, what applications are you thinking of in the future?
I can say that really this is characterizing to understand a process. I can't speak too much to applications, but I can say that just producing a body of measurements that can be used to validate and drive forward modeling and simulation and increase our understanding of filamentation at these longer wavelengths and in condensed materials in these glasses and crystals is something that is, as far as I can tell, lacking at this point. And so we're just trying to kind of whack out a frontier.
No, that's fair. And actually, just play off that real quick. We had a couple questions that came through in the chat function. And one question / comment said, hey, this is out of my depth, but I'll ask if is this pure R&D or does it have an objective like altering microbiological targets or for communications or something like that?
I think
go ahead.
I can say that there are pure there are applications and that there are just for the basic research aspect of it.
Yeah, and then the other question comment related sort of along the same line was, does this have any would this have any interaction with personal protective equipment like such as polycarbonate or anything that would protect you? Again, probably more application based than you're aiming at, but just thought I'd throw it out to you.
I mean, that is important to understand, especially if there are materials that one would think would be protective, but then that would be protective in a linear regime, but then have different behavior with pulsed lasers and with nonlinear effects taken into account. It's important to know that and understand that.
Yeah, perfect. Okay, let's move on here. The next question we had was, is the data in the long wave region using MCT not interesting and thus not presented?
So that is much more difficult. So the measurements, we haven't gotten to needing those yet. So if you look at the spectra on the long wave side, they all have kind of the same tailing off behavior that you can project pretty easily. At the farthest we've gone right now is 1.3 microns because of our experiments kind of got interrupted. But the farthest we've been able to go to this point is 1.3 microns. But as we move forward and starting at 1.3 microns, 1,000 nanometers of spectral broadening to the right is still a massive continuum. But we haven't gone to the point where we needed to jump to that MCT detector yet. Moving forward, the next step is just marching down to longer wavelengths, 2, 4, and when we do move there, we will need to use the MCT detector. But it's at the moment the supercontinua are not reaching out that far in an interesting way yet, and so it's just not necessary to add the third layer of spectrometer stitching together on top of it to get what's basically just going to be a tiny little tail in the noise. But once we do move to the next longest wavelength, it will definitely become necessary to incorporate. And again, we've got that spectrometer set up and calibrated and ready to do the measurements. They just weren't necessary at these primary wavelengths.
Okay, great. So we're getting close to 12:45. Let's maybe do two questions, 3, depending on how quickly they go. And I apologize for anybody else's question we might not be able to get to today. So let's just jump to the next one. Are the experiments conducted in air, or is the beam path in vacuum for these studies?
The beam path is in air. I've been looking into whether I need to isolate the beam. Right now, there's a propagation distance between where it's generated in the OPA and where the focusing starts, the pre-focusing into the sample. I was going back and forth, but right now, rather than trying to vacuum isolate the beam all the way to the sample, I am just characterizing the beam, measuring the spatial beam and the power at the beginning of the experiment, at the lens, and as it focuses down toward the sample to give the basically to kind of ignore everything that's happening between the source and that first lens, and just take that first characterization as the starting point. That's not ideal, but isolating the beam would be complicated, and so I'm hoping that that's enough.
Okay, great. Next question: how do you differentiate between multiple filamentation from gratings that scatter?
Not sure I understand the question. Sorry.
Yeah, I was wondering that as well. Well, that's okay. What else we have in queue? Well, the other ones in queue are not particularly deep in terms of constructive comments, but one question that's asked in the chat is what software is being used for your simulations?
So the only simulation presented was pulled from an example in the literature. It's a very good review by Gueron from last year or the year before. Our collaborators have developed a UPP code that is kind of its own executable. Again, I'm not the one running that. We have some people on at the lab that are learning it and running it, and we're collaborating with the team at University of Arizona to hopefully use the data and merge the data and the simulations. But at the moment, I'm not doing any simulations. I'm pure experimental.
Okay, fair enough. And then I guess the last question here, a minute or so, we have a couple left here. This came in the chat. So what would change with a chirped pulse amplified source?
So I mean the 800 nanometer TiSAF laser is a chirp pulse amplified source. They might mean, instead of going through an OPA and a DFG, just using a direct OPCPA. Those systems look very attractive. They are they've got, from what I've seen on the showroom floors and stuff, they've got great power, great stability. That's not the system I have. Theoretically, light is light. It should, to the extent that you characterize it, I think that you should be able to. I'm trying to make sure that I'm not saying anything dumb here, but yeah, I think that aside from them being, you'd be able to much more easily generate the pulses, and they are probably more stable, and you might get more power, but for the given laser powers and characterization at the start of the experiment, I'm pretty sure that it would just be the same.
Okay, no, fair enough. Well, hey, unfortunately we're bumping up against time, and I want to respect everyone's time, so I'm gonna cut it off here. But I do see some other questions that have been asked, so I would ask if there are any remaining questions, you can reach out to DSIAC. Go to our website. You can submit a technical inquiry for us to field for you. I'm sure Zach wouldn't mind any questions going directly to him to respond to as well. But be happy to interact with them if you have any further questions you want to toss our way. And with that, again, thank you all very much for sticking around, for joining in on this. It's being recorded. We'll make it available, and you'll see a follow-up email about that shortly. So thank you very much for your time, Zach. Thank you for your time. Have a great rest of your day.
And thank you very much for the invitation, and thank you everyone for watching and participating.